In this hour, we become more familiar with phasor domain analysis through some simple examples. Okay. This is our first example, where we have the following topology. And there are two inputs that are driving the circuit. Okay, both oscillating at the same frequency. Here we have our voltage source, and here we have our current source. Cosine 2t plus 45 degrees amps. Okay. Henry, 1 ohm, Henry, farad, and 1/2 ohms. Okay, we ask for the voltage across the terminals of the 1 ohm resistor in steady state. Okay, so find the steady state voltage across the 1 ohm resistor. Okay, so circuit is LTI and both inputs are oscillating at the same frequency, 2 radians per second. Therefore, we can easily analyze the circuit using phasor domain analysis techniques. Okay, so let's therefore, as our first step, transform the circuit given in time domain to phasor domain, where all the farads and henries transformed into ohms, and we obtain an LTI resistive like circuit. Okay, so this is our circuit, where everything now, all the components, the passive components, are represented by their impedances. Okay, so here we have 6 volts. Okay, the magnitude is 6 and phase is 0. Therefore, this produces a 6 volt source in phasor domain. Here we have 45 degrees amps. So that's how we represent our current source in phasor domain circuit, and the remaining components, let's now for them find their impedances. Okay, so here we have an inductor with 0.25 henries. In phasor domain circuit, its impedance becomes j omega L. Okay, omega is 2 and L is 1/4, therefore we have j 1/2 ohms. Okay, so here we have henries and now it becomes ohms. So that's the whole beauty in phasor domain analysis. And then as for resistors, you directly carry their resistances to phasor domain. Okay, so here we have 1 ohm, here we have 1/2 ohm resistor. For this inductor, 1/2 Henry, so we have j omega L, omega being 2, gives us j ohms, and finally for the capacitor, the impedance is 1/j omega C. So this therefore produces j2 ohm impedance for the capacitor. Okay, so this is our phasor domain circuit. Since it's just like an LTI resistive circuit, we can solve it any technique, using any technique we like. So let's apply therefore node analysis. Okay, so let's pick a ground node and then mark the remaining nodes. Here we have E1, here we have another node, here we have E2. But since these two impedances can easily be combined into one, okay, J plus minus J2, so that makes minus J. We don't have to really assign a node voltage to that node because we're asked for the voltage across terms of 1 ohm resistor. In other words, we're asked for E1. Okay, so with two formulation variables, we should be able to formulate nicely this phasor domain circuit. So let's write down KCL at each node. At node 1, here we have this current plus that current equals 0. So what's this current? That current is E1 minus 6 over the impedance in between, which is J 1/2 ohms, okay, plus this current, which is E1 over the impedance, which is 1, and finally this current, which is E1 minus E2 over the impedance in between, which is J plus minus J2, which is minus J. And since KCL holds in phasor domain, that sum must equal 0. So this is our equation, or node equation 1. Okay. Now, for node 2, we're going to do the same thing. We have E2 minus E1 divided by minus J plus E2 over 1/2, and finally this current, which is minus 3 square root of 2 with phase 45 degrees equals 0. And that's our second node equation, equation 2. Okay. So by dealing with these equations, we can easily obtain E1, and then once we have E1, we can figure out E1 of t, okay, lowercase E1 of t, and then that's what we're asked for. That's the voltage that we're after. Okay, so let's rewrite equation 1 and simplify it a little bit. We have for E1 terms minus J2 plus 1 plus J. Okay. This produces minus J2. We have 1 here, and then this minus J carries upstairs with plus J. So that's the coefficients of E1. As for E2, we have minus J. Okay. Only this guy here. And then what we do, we take this term, minus 6 over J 1/2 to the other side, and that produces minus J 12. Okay. And then after simplification, this produces E2 in terms of E1, which reads minus 1 plus J E1 plus 12. Let's call this equation 3. Okay. And now, dealing with equation 2, we can write minus J E1 plus 2 plus J E2, okay, equals this guy thrown to the other side. So let's write this in rectangular form. It's given in polar form, which is easy to write because we have a special angle here, 45 degrees. That's 3 square root of 2 magnitude with phase 45 degrees can be written as 3 plus J3. So therefore this equals 3 plus J3. Okay, so this is our equation 4. Now let's combine equations 3 and 4 to obtain E1. 3 and 4 produces minus J E1 plus 2 plus J E2, okay, and E2 is here. Right, 12 minus 1 plus J E1, okay, and that equals 3 plus J3. Now the equation is only in terms of E1. After some manipulations, we can write this to equal minus 1 plus J4 E1 equals minus 21 minus J9, if I haven't made a mistake somewhere, from which we have E1 equals what? 21 plus J9 over 1 plus J4. That can be written as 3 over 17, 19 minus J25. Okay, equation 5. Now we have E1 in rectangular form. We're going to transform that into the polar form, which will give us the magnitude and the phase. Okay, and once we have the magnitude and the phase, since the frequency of oscillations was 2 radians per second, we will easily be able to write down E1 of t. So let's do that. Let's do that final step. Finally, okay, equation 5 yields E1 of t equals. Okay, so what's the magnitude of that? It's 3 over 17, and then we have 19 squared plus 25 squared, so that's the magnitude. As for the phase, it's arctangent minus arctangent, 25 over 19. Okay, therefore, the phase of our cosine, which is oscillating at 2 radians per second, because that was the input of the frequency of the inputs, is minus arctangent, what, 25 over 19 volts. Okay, so that's the voltage across the terminals of 1 ohm resistor in steady state. Okay. Let's move on to our next example. Which contains an operational amplifier. Okay, our example is given as follows. So we have a source here, 5 cosine 3t volts. Okay, a sinusoidal input oscillating at frequency 3 radians per second. And then we have a capacitor. We have another capacitor that is connected to the op-amp, which we will assume to be ideal. Okay, minus, plus. Here we have the feedback connection to the output node. This is our out T. And here we have another feedback connection. Okay, 2 ohms. The capacitances are 1 over 12 farads each. And here there is another connection of 2 2 ohms. Okay. Now, for this circuit, we're asked to find the output voltage of the op-amp, assuming that op-amp never enters the saturation region and always remains in the linear region. Okay, so assume that op-amp is in linear region and the circuit has reached sinusoidal steady state, and circuit is in sinusoidal steady state. Okay, under this assumption, we will now try to figure out, using phasor domain analysis, the output voltage produced by the operational amplifier. Find V out T. Okay. So we're going to do the same thing. We're going to transform this circuit to phasor domain equivalent, where we replace the capacitances with, or represent capacitors with the impedances, their impedances, which is 1 over j omega c. C is 1 over 12 and omega is 3 radians per second. And then everything will be in terms of ohms, and then the circuit will become linear, time invariant, resistive type. And then the analysis is quite straightforward. And once we figure out the phasor of the output voltage, all that remains is, using this frequency formation, we're going to obtain the time domain signal. Okay, here is the phasor domain circuit. Okay, 5 volt, and here we have our first capacitor, here we have our second capacitor, the op-amp, this is the output voltage. Resistor, and we have the feedback connection, and we have here and the other feedback connection. 2 ohm. Okay, so as for resistors, their resistances directly carry to phasor domain. They're independent of the frequency, whereas the impedance of a capacitor or the impedance of an inductor, they depend on the frequency of oscillations. In our case, frequency of oscillations is 3. The impedance of our capacitor is 1 over j omega c. 1 over j omega c. C 1 over 12, omega 3. Therefore, that produces minus j4. Okay, and this farad becomes nicely ohms here. And same holds true for the other capacitor. Now we have everything in terms of ohms. And now it's easy to obtain the equations which will eventually lead us to the output voltage, V out. Okay, so let's call this node voltage V1. Okay, now since op-amp is in linear region, V minus and V plus voltages, they are the same. Since due to this feedback connection, the voltage of V plus is V out, this voltage must also be V out. So we can put here V out. Okay. To write the equations, we write KCL here, and then we're going to write KCL here, and then we're going to cancel V1 and obtain V out. So writing KCL in this node equation yields the following: V1 minus 5 divided by the impedance in between, which is minus J4. Okay, and then we have this current, which is V1 minus V out divided by the resistance in between, which is 2. And finally, we have this current, which is V1 minus V out over the impedance in between, which is minus J4. Since KCL holds in phasor domain, this sum must equal 0. This is our first equation. Okay, let's simplify this equation. We can write 1/2 plus J 1/2 for V1 and 1/2 plus J 1/4 for V out, and the right hand side is J 1.25. Okay, this is our equation 1. Let's write the other node equation in this node. Okay, we have V0 minus V1. Okay, we have this current and we have that current. This current is V0 minus V1 over minus J4. Minus J4. Okay. Plus this current, which is V0 over 2. And finally, we have this current, but we're dealing with an ideal. We're assuming that the op-amp is ideal. Therefore, the input resistance is infinite, meaning that we have no current through that wire. So that's the whole set of currents, and then by KCL, that must equal 0. Okay, this yields, after simplification, V1 equals 1 minus J2 V0. So let's call this our equation 2. Here we have equation 1, and there we have equation 2. By replacing V1 here by the expression here, 1 minus J2 V0, we can obtain an equation only in terms of V0, and from that equation we can pull V0, the phasor of the output voltage. Once we have the phasor, write it in polar form, and then it's straightforward to obtain the time domain signal. Okay, so combining equations 1 and 2 implies, okay, so we have what? 1/2 plus J 1/2 times V1, and V1 is 1 minus J2 times V0, 1 minus J2 times V0. And what else we have? Minus this times V0, minus 1/2 plus J 1 over 4 times V0. We can take both V0s out and write it as such. And then what we have this right hand side, so that equals J 5 over 4. And then this chunk here, simplified, yields 1 minus J 3 over 4. Okay, that equals J 5 over 4. Therefore, V0 is this divided by 1 minus J 3 over 4. Since we're going to do a division, let's transform this, in fact both sides, to polar representation. So what we have here is, here 1 squared plus 3 over 4 squared, and then you take the square root. The magnitude of this complex number is 1.25. Okay, so what we have is 5 over 4. The phase is arctangent, or minus arctangent 3 over 4. Minus arctangent 3 over 4 times the output voltage equals, let's write this also in polar form. The magnitude is obvious, it's 5 over 4. How about phase? Okay, J can be written as e to the j pi over 2, therefore the phase is 90 degrees, or pi over 2 radians. So this is 5 over 4 with phase 90 degrees in polar representation. And this immediately yields V out equals, okay, since both sides are in polar form, division is straightforward. We have 1 as magnitude, okay, And as for phase, we have 90 degrees minus this phase, which is minus minus arctangent 3/4 plus arctangent 3/4 volts. Okay, equation 3. We have the output voltage in polar form, therefore it's easy, straightforward to convert it to the time domain representation. All we have to do is we have to remember the frequency of oscillations, which was in our case 3 radians per second. So the out T is a sinusoidal signal with amplitude 1. Okay, frequency of oscillations 3 radians per second, and phase equals 90 degrees plus arctangent 3/4 volts. Okay. Now, before we move on to our next example, let's consider a slight modification of what we have just considered from the input point of view. And the slight modification, by slight modification, I mean the following. Okay, question. Suppose that everything is the same with our op-amp circuit. The only difference is that we start timing our input, okay, voltage, from a different starting point. In other words, the phase of our input voltage is different. Okay, what if Vs of t, the input to our circuit, is different, and that to indicate that difference we put a little tilde over there, and instead of 5 cosine 3t, it is 5 cosine 3t plus some phase. And without loss of generality, we can take any phase we want. Let's take 23, some arbitrary prime number. Okay, volts. Now, the question that we want to answer here is the following. Suppose that we did our computations, and they're already on the board, for 5 cosine 3t input, and this is our answer, okay? That's the output voltage. Now the question is, if the input is slightly changed by adding this phase, do we have to do all our calculations once again, or can we use this already computed output information to compute the output that would correspond to Vs tilde t, namely V out tilde t? And the answer is really simple, which is that we don't have to recompute everything, because adding a phase or subtracting a phase to a signal in phasor domain, okay, corresponds to just multiplying with a scalar. So let's figure that scalar out, and that will immediately give us the phase that we should add to our previously obtained answer. Okay, so what we have is the following. This is our phasor domain circuit. Okay, let's call it N. To the circuit we have an input, okay, let's say our voltage V of S. This is our input, and this input generates an output, which we denote by capital V out, output. Okay, so this is representing the case in phasor domain. Now, by linearity, because the phasor domain circuit is linear, we have to have the following. Okay, the same circuit N, and this time we add, or we derive the circuit with Vs tilde, which is a scaled version of the first input, okay, Vs. So alpha times some Vs. So due to linearity, if this is the input in the second case, the output must be the scaled version of the first output, and the scaling factor is alpha. Okay, so here we should have V out tilde must equal alpha times V out, directly due to linearity. Okay, now let's consider this question once again under this property, scaling property given us by linearity. Okay, we can write the following: Vs tilde t. This is our new input, which is 5 cosine 3t plus 23 degrees volts. The old input was 5 cosine 3t, no phase or zero phase. Now this Vs tilde produces the following phasor, equals 123 degrees. Okay, so here we have a complex number with magnitude 1 and phase 23 degrees times Vs. Okay, so this is Vs tilde, clearly. Because multiplying Vs by this simply would add 23 degrees of phase to Vs, and that's what we want, really. So, if this is our alpha, V out tilde must be the same alpha times V out obtained earlier. Okay, 1 phase 23 degrees times V out. And what V out was the following number. The magnitude was 1 and the phase was 90 degrees plus arctangent 3/4. That was our V out, and then we're multiplying that V out with this alpha, which would simply add a 23 degrees to the phase. Okay, so that means the output that we would compute or we would measure when we drive the circuit with the new input Vs tilde, which has an extra 23 degrees of phase compared to the original input, we will have the following output: 3t plus this plus that gives us 113 degrees plus arctangent 3/4, okay, radians. So that's our new output. Okay, so therefore whenever you have an input in your circuit like omega t plus some funny phase, you can just forget about that funny phase, okay, and consider phase-free or zero phase input, obtain the output that you ask for, and once you have the final answer, just add that phase that you omitted in the beginning to your final answer. Okay. Now, let's move on to our last example. which is a dynamic circuit with 3 dynamic components. Okay, so it's the order is 3. We have 2 capacitors and 1 inductor. We have 2 sources, both current sources. This is labeled IS1, this is labeled IS2. 4 ohms, 1/32 farads, 4 ohms, 4 henries, 1/32 farads, 8 ohms. Okay, and we are after this voltage drop across the terminals of this 8 ohm resistor. Okay, now what's given is as follows. We're told that IS1 of t is 6 cosine 4t amps. The second input is 2 cosine 40 amps. Note that they oscillate at the same frequency. Therefore, we will be able to get away with a single phasor domain circuit. And the circuit is known to have reached the steady state. Okay, it's in sinusoidal steady state. Under this information, find the voltage Vx of t, given as the voltage drop across the terminals of 8 ohm resistor. Okay, now we used node analysis in our previous examples. Therefore, let's apply mesh analysis for this last example, just to see that we can. Okay, here is the solution. Let's write down the phasor domain circuit, where the passive components will be represented by their impedances. This is our first input. Okay. This is IS1, this is IS2. 6 amps and no phase. Likewise, this is 2 amps and no phase. Okay, as for the impedances, we have 4 ohm, 8 ohm, and 4 ohm here. The resistances, they are carried directly to phasor domain. As for the capacitors and inductors, we have to compute impedances using the frequency information, which is 4 radians per second in our case. Okay, the impedance of the capacitor is 1/j omega. C omega is 4, C is 1/32, so that produces minus J8 ohms. Okay, and here we have another minus J8 ohms for the other capacitor. And for the inductor, impedance is J omega L. L 4, omega also 4, so that produces J16 ohms. Okay, now we have 3 meshes, but we don't have to assign a mesh current for the top mesh because it's directly known. Okay, so therefore we have to assign only variables, mesh currents, to the bottom 2 meshes. So let's call this IA, mesh current A, and let's call this IB. Okay. Now, let's write down mesh equation, but between those 2 meshes we have a current source. Okay, therefore what we do in such cases, remember, we just combine 2 meshes and write the KVL on the super mesh. So the super mesh equation therefore produces the following. Starting from this point, we have 8, and we have another impedance, they are in series, so that makes together, okay, 8 minus J8. So that's our first voltage drop, let's say 8 minus J8 times IA. Okay, then we have this voltage plus minus over the 4 ohm resistor plus 4 times this current. This current is IA plus 6. Okay, IA plus 6. And then we move on to the second capacitor. We have minus J8 times this current. This current is IB plus 6 minus J8 IB plus 6. And finally we have this voltage drop, which is IB times the equivalent impedance, which is 4 plus J16 plus 4 plus J16 times IB. And since KVL holds in phasor domain, the sum must equal 0. Okay, so we had two unknowns. We have written down a single equation. The second equation clearly will be coming from the constraint equation. Here we have a current source between two meshes, and its direction is up and value 2. What we have therefore is IB minus IA equals 2. Constraint equation reads IB minus IA, okay, IB minus IA equals 2, which allows us to express IB in terms of IA. IA plus 2. Okay, so this is our equation 1, and let's call this equation 2. By substituting IB in equation 1, what we will do, we will obtain IA, an equation only in terms of IA, from which we can solve for IA. Once we have IA, okay, we can easily compute this voltage Vx, which is 8 ohms times this current, which is minus IA. And then we have, once we have Vx, the frequency is here, 4 radians per second. We can easily write down the time domain signal Vx of t. Okay, from now on, the rest is just playing with the equations. Let me write down equation 1 once again. We have what? 8 minus J8 plus 4 IA. Okay, so we collected the IA terms under one parenthesis, plus minus J8 plus 4 plus J16 times IB, and that equals whatever remains we throw to the other side, and that happens to equal minus 24 plus J48. Now what we can do is we can replace this IB by IA plus 2, which is what we have obtained in equation 2. So let's write that down, IA plus 2. And now this equation is only in terms of IA. So that produces, after cancellations, 16 IA equals minus 32 plus J32, if I haven't made a mistake somewhere. And this yields IA equals minus 2 plus J2 amps. Okay, so we have IA. From IA, we can now write down Vx. Vx is this voltage plus minus. Therefore, it equals 8 times this current, and this current is minus IA. Okay, so Vx therefore equals minus 8 times IA, which is 16 minus J16 volts. Okay. Now, since we're going to transform this now to time domain, it's better that we write this in polar coordinates. So 16 plus J16 is, okay, let's remember the phasor diagram quickly. Real imaginary. Here we have our vector with real part 16 and imaginary part minus 16. So we're dealing with this vector minus j16. Okay, so this is our Vx. The magnitude of this vector is 16 square root of 2, and this angle here is 45 degrees. Since we measure by convention the angle starting from positive real axis and going counterclockwise, the phase of this vector 16 minus j16 is minus 45 degrees. So Vx therefore equals 16 square root of 2 with phase minus pi over 4 radians volts. Okay, and finally, all we need now is we have the magnitude, we have the phase, we need the frequency information, and the frequency was 4 radians per second. Okay, we have to go back to the time domain circuit. Hence, our signal in time domain is the following sinusoidal: 16 times square root of 2 cosine 40 minus pi over 4 radians volts.